Hello everyone, we start chapter 5, which introduces sequences, mathematical induction, and recursion. In the first section, we start with sequences and the definition of sequences. So, a sequence is a function whose domain is either all the integers between two given integers or all the integers greater than or equal a given integer. So there are two cases. In the first case, the domain of sequence, which is a function, is all the integers between two given integers. So let's see this example. am am plus 1, am plus 2, all the way to am. So this is a sequence of numbers with the domain m plus 1, m plus 2, all the way to n. And each of these individual elements like ak, which we can either read it as ak or a sub k, is called a term in this sequence. And so we have how many terms we have. This is one term, this is two term, three term, all the way to n plus n minus m plus 1 terms. So a total of n plus m minus 1 terms we have in this sequence. So the k in a sub k is called the subscript or index. M, which may be an integer, is the subscript of the initial term. So that's called am is called the initial term, and m is the subscript of the initial term, and n is the subscript for the last term, which we call it the final term, right? So as you remember in the definition of sequence, we said there are two cases. In the first case, the domain of sequence is finite, is between two integers, and in the second case, we said all the integers greater than or equal to a given integer. So in the second case, the domain of a sequence is not finite, is an infinite set. So this is an example of such case. In this case, the sequence has a domain of m plus 1, m plus 2, all the way to infinity. So we have an infinite number of elements in the domain of this sequence, right? That's why we call this sequence an infinite sequence. So again, this sequence has infinite number of terms. The first term is a sub m or am. The second one is a sub m plus 1. The third one is m sub m plus 2. And this list goes on and on to infinity. Also, we need to know that a sequence sometimes is represented by an explicit formula or a general formula. So a general formula or explicit formula of a sequence is a rule that shows how the values of a sub k depends on k. So basically the explicit formula is a formula that writes a sub k as a function of k. So let's see an example of an explicit formula for sequence A, A1, A2 all the way to infinity, and B1, B2, B3, B4 all the way to infinity. Let's see how their explicit formulas look like. For A, we have AK equal, or A sub k equal to k over k plus 1. For all integers, k greater than or equal to 1. So the first term starts at integer 1, so the first term is a1, and for b we have bi equal to I minus 1 over I for all integers I greater than or equal to. So the index of the first term or initial term is 2, not 1. In AK, the initial term has a subscript of 1, but for the second sequence, we start at integer 2. Now the question is compute the first 5 terms of both sequences. Let's see. For A, we write something like this. We say A1 is, instead of K, we write 1, so it becomes 1 over 2, which is 1 over 1 plus 1, which is 1 over 2. And for A2, we have 2 over 2 plus 1, because for in A2, K is equal to 2, so we substitute K with 2. In the third term, we have A3 or A sub 3 equal to 3 over 5. Then A4 is equal to A4 over 5, and A5 is equal to 5 over 6. So these are the 5 terms of sequence A. For the second sequence, we should start at B2. So B2 is I minus 1 over I here in this case is 2, so we have to say 2 minus 1 over 2, which is again 1 over 2. Then B3 is the next second term of this sequence. So B3 is equal to 3 minus 1 over 3, which is 2 over 3. B4 is 3 over 3, 3 over 4. B5 is 4 over 5. And B6 is 5 over 6. So as you see, the index of the the sequence is equal to the denominator, while in the previous example the index of AK is equal to the denominator. Okay, so as another example of sequences, consider this very interesting sequence, which is an alternating sequence. Here is the general formula. It's Cj equal to -1 to power j for every integer j which is non-negative, which is greater than or equal to 0. Okay, so the first term of this sequence is obviously C0 because j is greater than or equal to 0. So C0 is the first one. C sub 0 is equal to -1 to power 0, which is equal to 1 by the definition of power to 0. And then we have C1, which is -1 to power 1, because we need to replace j with 1, and -1 to power 1 is equal to -1. C2 is -1 to power 2, which becomes positive, so C sub 2 is positive 1. C3 is -1 to power 3. Again, it becomes negative because if you multiply -1 3 times to itself, the result becomes negative. However, C4 is -1 to power 4, which is 1, because if you multiply -1 4 times by itself, it becomes positive. So C4 is positive, and C5 is, as you see here, C5 is -1 to power 5, which is -1. Again, it becomes negative. So as you see, the C0 was plus 1, C1 is negative 1. C2 was plus 1, C3 is negative 1. C4 was 1, C5 is negative 1. So the values of this sequence oscillates between negative 1 and 1. That's why we call it an alternating sequence. And let's see another example. This example is a little bit harder. It asks us to find an explicit formula or general formula for a given sequence. Here is a given sequence. We have the first term of this sequence equal to 1. The second term of this sequence is negative 1 over 4. The third one is 1 over 9, then negative 1 over 16, then positive 1 over 25, negative 1 over 36. So as you see, again, all the terms of this sequence which have an even index are negative, and all the terms of this sequence which have an odd index or odd subscript are positive. So we again we have an alternating sequence very similar to the example 512 that we just saw. So it should have a very similar explicit formula. So to summarize, I can write it like this. I can say a sub k is equal to plus 1 over k square if k is odd, and negative 1 over k square if k is even. The reason is, if you look at the denominators of all the given terms of this sequence, they are all perfect squares. So I conclude that this, the denominator should be in the form of a k square, where k is an integer, right? And the denominator is positive 1 for odd, for terms with odd index, and is negative 1 for those terms with even index, right? That's why I put the denominator as negative 1 to power k plus 1. So it is very similar to example 512, but in this example we have also a denominator which was a perfect square. That's why we put it k square. So now we can check to see if this this general term is correct or not. To check that, we have to first replace k by 0 or 1 to see if we can get the first term. If you replace this by 1, if you replace k by 1, then you get the first term, which is 1. If you replace k by 2, then you get the second term, and so on. If you replace k by 3, you get 1 over 9, and so on. You can continue doing this to check that all the 6 initial terms of the sequence that are given can be generated using this explicit formula that we obtained, and as a result you conclude that your solution is correct. Okay, so we continue chapter 5 by a definition. We say if m and n are integers and m is not greater than n, then this symbol, which you can read it as the summation from k equals m to n of a sub k, this symbol is the sum of all the terms of the sequence ak from the index m to index n. So it's equal to a sub m plus a sub m plus 1 plus a sub m plus 2 all the way to a sub n. Okay, so this is called the expanded form of this summation, and as I said before, we call k as the index of the sequence, and also we call it the index of the summation, and m is the lower limit of the summation, and n, which we put it in the top of this sigma symbol, is the upper limit of this summation. Okay, so as an example, let's look at three summations, assuming that a1 is -2, a2 is -1, a3 is 0, a4 is 1, and a5 is 2. We can compute these three summations. In case A, we have the summation of ak, k from 1 to 5. So in this case, we have to add all the elements of I together. So we have a1 plus a2 plus a3 plus a4 plus a5, which is equal to -2, which is a1, -1, which is a2, 0, which is a3, 1, which is a4, and 2, which is a5. If you add them all together, the result becomes 0. So the summation of a sub k, k from 1 to 5, is equal to 0. In part B, we have the summation of a sub k, k from 2 to 2. So in this case, we only have one number, and we basically don't have any summation. We only have the element a sub 2, which is equal to -1, because the lower limit and the upper limit of the summation are both equal to 2. So in such cases, please note that the summation becomes only one element of the sequence, one term of the sequence, because as I said, the lower limit and upper limit are equal. In the last case, we have the summation from k equal to 1 to k to 2, and we have a2k. So 2 times k is the subscript or index of a, or index of our sequence. So if you replace k by 1, you get a2 or a sub 2, and if you replace k by 2, you'll get a sub 2 times 2, which is a4, and a2 plus a4 is obviously equal to -1, which is a2, plus 1, which is a4, is equal to 0. As another example of summation, let's see this example where the sequence is given by the explicit formula. So we have a summation from k equals 1 to 5 k squared, right? So to calculate this, we have to first expand it. So it's going to be k equal to 1 square, which is 1 square, plus k equal to 2 square, which is 2 square, plus 3 square, plus 4 square, plus 5 square. If you add all these 5 numbers, you will get 55. So this summation is equal to number 55. Okay, so similar to what we defined for summation, we have another definition which defines the product of the number of terms of a sequence. Here is the definition. We say if m and n are integers and m is not greater than n, then the symbol product from k equals m to n of a sub k is the product of all the terms a m plus 1, a sub m plus 2, all the way to a sub n, and we say that this multiplication, this product, is the expanded form of the symbol that I just introduced, right? So let's see another definition which utilize the symbol that I just defined. We say for every positive integer n, the quantity n factorial denoted by n, and then you see factorial, is defined to be the product of all the integers from 1 to k, right? So n factorial is product of k from 1 to n k, and the expanded form is n times n minus 1 times n minus 2 all the way to 3, 2, and 1. So if you multiply the first n positive integers, you will come up with the n factorial, okay? So we also define factorial for 0. We say 0 factorial denoted by this symbol is defined to be 1, right? So for 0 we have a separate definition, and for all other integers greater than 0 we have another definition. After defining factorial, we define another symbol. So if n and r are integers and n is greater than or equal to r and both of them are non-negative, then the symbol n choose r represent the number of subsets of size r that can be chosen from a set of size n. Okay, so I'm not going to go to the details of what the definition is, because we will talk about this in detail later, but I just want to show you the expanded form of n choose r, which uses factorial. So that's a good example for you to know in this chapter. So n choose r is equal to a quotient where the numerator is n factorial and the denominator is r factorial times n minus r factorial. So if you write the expanded form of factorials, the denominator becomes n times n minus 1 times n minus 2 all the way to 1, and the denominator becomes two parts. The first part is r factorial, which is r times r minus 1 all the way to 1, and the n minus r factorial part becomes n minus r times n minus r minus 1 all the way to 1. So the next step, I'm going to separate the denominator into two parts. You see, in the denominator we have multiplication of all the numbers from 1 to n. So I'm going to divide this product into two parts. The first part is multiplication of all the numbers from n to n minus r plus 1, and the second part is multiplication of all the numbers from n minus r all the way down to 1, right? So I just you know, divided the denominator into two parts. I didn't change its value, so I would also don't touch the denominator. I just write the denominator as it is. Now, as you see, this multiplication, this product in the denominator and this product in the denominator will cancel out each other. So what we will get is a product like this over r factorial. So I write r factorial in the denominator, and I write the product in the denominator using the symbol that we just introduced. So I write product of k from n minus r plus 1 all the way to n, and the sequence is k because we are just multiplying all the numbers from n minus r plus 1 all the way to n. So for the sequence, we just need to write k. That's the explicit formula for the product of the denominator that we obtained. So this is the whole thing. The whole quotient is the expanded form of n choose r